couple of things I want to add here. If we kind of turn this sideways so I can write a little bit better. Note that we're going to have some rock types, right? So for volcanic rocks, the mafic rock is called basalt. Right? I'll do more of this later, but just to kind of get this table filled out. Then the intermediate volcanic rock is called andesite. And then finally, the felsic volcanic rock is called rhyolite. And what I want you to understand is that these are extrusive volcanic rocks. They erupt from a volcano or they explode. They're somehow coming out of a volcanic vent. Now, they have plutonic equivalents, right? So remember Pluto, the Roman god of the underworld, right? Roman god of the underworld, living down at depth, right? So these rocks cool, solidify, freeze at depth, right? And make plutonic rocks. So the chemical equivalent of basalt that cools at depth is called a gabbro. Gabbro. The chemical equivalent of andesite that cools at depth is called diorite. And finally, the chemical equivalent of rhyolite that cools at depth is called granite. So those are our rock types. Basically, there's basalt, andesite, rhyolite, gabbro, diorite, and granite. All right, so the next part here discusses settings for extrusive rocks, right? And so these are going to erupt from a volcanic vent. The key thing is we have a vent, you know, where this magma is going to come out onto Earth's surface, right? And the type of eruption depends on the chemistry of that magma plus its volatile content, right? So felsic magmas tend to be volatile rich. They're viscous, right? And they have high silica content. So when they erupt, they're usually explosive, right? And they form thick ash deposits and ash clouds and maybe some pyroclastic debris columns coming down. So these, you know, when a felsic volcano erupts, you don't want to be very close to these. You want to be far away, observing from tens of kilometers away. Now, for mafic magmas, they have less silica content, right? Because they have more magnesium and iron. They have a lower viscosity, which means they're more fluid, and they tend to trap fewer volatiles, right? So when they erupt, because they have fewer volatiles, they're less explosive. Because there's less gas, less explosive. And so, you know, here I say, think of Hawaii. You can pay people money to fly you in a helicopter right over a volcanic eruption in Hawaii, right? You would never want to do that over here with a felsic volcano. You'd get vaporized. Now, and again, these mafic eruptions tend to spread in broad, thin lava flows, right? Because they have a low viscosity. They're pretty fluid. Now, when we think of intrusive settings, magma moves upwards, it percolates between grains, or it may make these tension cracks forcing rocks open. And so when geologists look at intrusive rocks, we just distinguish them based on the shape of the intrusive body, right? And so for the first one, we'll look at some tabular sheets here. And for a tabular sheet, we're thinking a planar shape. And there's two types. There's a dike and a sill, right? So dikes are said to be discordant intrusions. They cut across existing strata or foliation, right? And so these dikes are cutting across the existing material and are discordant to that already existing layers, right? And now a sill is a concordant intrusion that's injected parallel to layers. And usually this occurs at shallow areas where the force of that intruding sill can push that rock up, right? And so in fact, let's look at an example. Let's say we have some strata here, some rock layers. And so the discordant intrusion would be a dike that comes up from submagma chamber here, right? So note that this dike here cuts across existing layers, right? So that would be our dike. Now, for a sill would penetrate parallel to layers here, right? Parallel to layers here. And so the sill would be in between these layers, a sill. And in some cases, if the sill kind of bubbles up, kind of like this here, and causes a change in some of the strata here as well, we see that this here would be the laccolith, right? So that would be the laccolith right there. So some sills inject between sedimentary layers, but then dome upward, forming laccoliths. All right, so sills and laccoliths. So concordant because it conforms to the existing. In fact, remember this stuff I call the country rock. Your book calls it wall rock, but it's the same thing. And then the dikes are discordant. They cut across those. Now, in terms of plutons, these are blobs. They're tear-shaped diapirs, and you can think of a diapir like I have here, almost like a balloon rising here, right? Expanding as it's moving up on its way toward the surface, right? This diapir. And these can be anywhere from, tens of meters, 50, 60, 80 meters across. And some are on the order of kilometers, 10, 30, 50 kilometers, some of them in the Sierra Nevada. They're quite huge. When you get numerous of these plutons that coalesce together, 40 or more, and they cover an area of over 100 square kilometers, these are called batholiths. Remember, this term bath is deep in Greek, and lith is stone. So again, plutonic forms at depth, right? And an example of a batholith is our Sierra Nevada batholith. I'll say more about this in the next video here. And then remember, these diapirs may rise. They can force the overlying wall rock aside, and so that must mean there must be some extension, right? In fact, there's a diagram here showing some of that here, and so this is figure 411 in your book. So you can see that these plutons move up through the crust and they expand, and you might see some crustal extension as these diapirs or plutons are moving aside this magma or this existing country rock. Other things that may happen to get these plutons up toward the surface or shallower levels in the crust is you may see stoping. And stoping is basically pieces of the country rock falling down into the magma chamber, right? And so when stoping occurs, some of that magma that falls in, or some of that country rock that falls into the magma may be assimilated, right? And if it's assimilated, then the chemistry of the magma will change. In some cases, let's say we have some wall rock here. We'll put some layers, and let's put a magma chamber in here, right? So here's our magma, and then we'll have our surrounding strata here, our country rock or wall rock here. So this wall rock, I'll put wall, country rock. Let's say a piece of this wall rock stopes and falls in here, right? So we'll put a layer of strata in there. So a piece falls in, but it's not completely assimilated, right? It's not completely. So when that happens, that's called a xenolith. And xeno means foreign stone, right? A foreign stone. And so the foreign stone is obviously a different rock. All right, so I'm going to show you some of the figures in your textbook that relate to some of these igneous intrusions, right? So in figure 4.9, we're looking at some sills and dikes, or examples of tabular structures. So this is an example of the sill, which would be parallel to the existing layers, right? Concordant, whereas this would be the dike. And remember, see, it is a tabular feature, and note that it cuts across the strata. It's discordant, right? And so here's kind of another picture showing some pre-existing country rock or wall rock where a dike intrudes, cuts across through it. And here is a large-scale intrusion of a sill that is several meters thick, right? But it's going parallel to the country rock here, to the wall rock. And then a really famous volcanic neck or intrusive feature in the western United States is this place here called Shiprock, which is in northern New Mexico. It's really the four corners areas of the western United States. And you can see Shiprock is a volcanic plug, right? So it's the neck of a volcano. This volcano is much larger here before, but it's eroded away. And you can see that there's these radiating dikes. There's one going off this way, another one going off that. But again, they're planar intrusions. A dike here, and a dike over there, right? So that's some examples of some dike features. Now, if we go over here to the next page, figure 410, it shows some body shape intrusions, right? So it's showing basically several plutons down here coalescing to form a batholith, right? So this would be the batholith down here. And then here's some individual magma chambers that are still molten, but they're giving rise, they're sending up sills through here, dikes. In fact, I probably didn't mention this one, but this is a special type of dike here. This dike that feeds magma to the volcano is called the feeder dike. The feeder dike, right? So there's feeder dikes, there's sills. Here's a dike that comes up here that ends up ponding into a sill that eventually forms a laccolith, right? And then some relationships we see over here. We see heat from the intrusion bakes. So we have this bake zone out over here. An intrusive contact, the contact between the intrusion and the wall rock or country rock. They have an image of the Sierra Nevada batholith, right? So the Sierra Nevada is a batholith. And you can see sort of later on we'll talk about this structural feature called exfoliation. It's more of a geologic structure. And then here is showing another contact between a granitic rock, which used to be a magma chamber, and it's wall rock or country rock back over here. And so you can see there's a little bit of bake zone going on there, right? And then the last thing to finish up, the Western United States does have large batholiths. A really famous one here is the Sierra Nevada one that's really close to us. And it's really a continuation of a southern one that's down in Baja California called the Peninsular batholith down here, Peninsular batholith. And then you can see there's the Idaho batholith over here, and then the Coast Ranges batholith, which is very extensive, right? Again, all these are Mesozoic in age, and when we start doing geologic time, we'll say more about them. Okay, well, we'll stop here for now.